I'd like to go over what exactly intermolecular forces are. There are dispersion forces, dipole-dipole, and hydrogen bonding ion-dipole. Know that, again, these are the glue that holds everything together. Okay, so what makes a solid a solid? Why is it held together whereas gases are very spread out and the molecules are not very close together? So it's the attraction of molecules to other molecules. The first one here are dispersion forces. Basically, so it's the attraction of protons of one molecule to the electrons of another molecule. Okay, so I'm showing right here, or actually it's not a very good picture. Let me go to this one, I guess. It's the same picture. Okay, so here is the nucleus of one atom, and it has, protons in it. And obviously it's attracted to its own electrons, but we don't care about that. We want the attraction to another molecule, okay? So the protons here are attracted actually to the electrons of another molecule. Same here. The protons in this nucleus are attracted to the electrons in this molecule. So basically, the protons in this molecule are attracted to the electrons in this one, and the protons in this one are in the other molecule right here are attracted to the electrons here. So basically, since everything has protons and electrons, everything has dispersion forces. Okay, so it's the attraction of protons of one molecule to the electrons of another molecule. Okay. Oops. There are trends. Okay. First of all, sometimes I just shorten it to dispersion forces instead of London dispersion. Dispersion forces increase with increasing molar mass. Okay, so let's think about why that would happen. Or what we're looking at is protons and electrons. Okay, does it make sense that the larger the molecule is, or you want to say it weighs more, the more protons it has, right? So if you have more protons, then you have a stronger magnet if you want. So the heavier something is, the greater the molar mass, the more protons you have, so therefore you're the stronger intermolecular force or dispersion because you have more protons. Also, dispersion forces increase with increasing area to interact, okay? So again, these intermolecular forces, and we're looking at dispersion forces specifically, they're like glue. They're attracted to each other, so they want to get as close to each other as possible. So let's look at here. Do you see that these branches kind of block things from getting close to it? Okay? And there's not as much surface area as exposed. Now look here, this one just has one branch, so it's not as quite as blocked. This one has 0 branches, and you see all this surface area that's exposed here. And so this is the maximum amount of interaction you can have. Basically, all the protons and electrons are exposed, so you're going to have the maximum interaction. Versus here, they're blocked a little bit, so there's not as much surface area there. So basically you want no branching, and branching is like when you have like these lines coming off of here. Okay, so for dispersion forces you want to be really large, okay, so have a lot of carbons, hydrogens, nitrogens, oxygens in it, okay, and you want to have no branching. So let's look at some examples. Let me draw. Okay. If we have something like this, versus this, okay? And just so you know, these are carbon chains. Every end and point is a carbon, okay? So you haven't seen this before. But can you see that this one is longer than that one, okay? So which one would have the stronger dispersion forces? The answer is this one because it's bigger, okay? Because it's bigger, because it has strong dispersion forces, that means it's going to have a higher boiling point and melting point, okay? These are a measure of how hard it is to break the molecules apart, okay? So basically, how much energy it takes to break the intermolecular forces. So whenever they have very strong intermolecular forces, that means it's going to take a lot of energy in the form of heat, like a boiling point or a melting point, to break them apart. Okay, so let's look at this one. Let's see. This one might confuse you. Hydrogens don't count in branching, by the way. We sort of usually ignore them. Okay, so basically, this has 2 carbons. This is what I would look at. Size is the most important, then look at branching. This has 2 carbons, this has 3. So which one's bigger? This one. So it has the stronger intermolecular forces and a higher boiling point and melting point. If we look at branching, it might be something like this. Versus, okay, so which one has the most branches coming off? Do you see this one has 2 branches off the main chain? This one has 3. It has, a branch coming off here, a branch coming off here, a branch coming off here. So the highest one with the least amount of branches is right here. Okay? So that's dispersion. It's basically attraction of the protons in one molecule to the electrons of the other. And the trends go, you want a larger molecule because more protons, and you want the least amount of branches because the branches block the interaction. Okay, let's look at another one. So those are dispersion. Let's look at dipole-dipole. This is the interaction of a partial positive end of one molecule to the partial positive or partial negative of one molecule. Okay, so let's look at this. First of all, you have to have a polar molecule, okay, and you have to have an electronegative atom in there. So if we look at, we have the example there is ICl. Okay, I'm going to write it like this on purpose. Okay, out of those, which one's the most electronegative? And whichever one is closest to fluorine is the most electronegative. And if we remember, electronegativity is the attraction to electrons. So they want a lot of electrons. Chlorine is the most electronegative, so we put this partial negative sign above it. That just signifies most electronegative. This one's the most electronegative, so we put a partial positive. Again, chlorine's the most, so partial negative. And this one will get a partial positive because it's the least electronegative. Okay, now think about magnets. Does it make sense that the negative end here, so this partial negative, will be attracted to the partial positive there? So we kind of draw this attraction usually with these lines. These are attracted to each other. Now this positive end is going to be attracted to the negative end. Okay, so this is a pretty strong intermolecular force there. Dispersion is your weakest one, and your dipole-dipole, and sometimes I just say dipole, is your next strongest, if you want. So I brought this one up here. You see? So again, iodine there is a partial positive attracted to the partial negative, just as I've drawn it. You can also look at it this way. They can interact in this way where they have just attracted at one end. It doesn't matter. So some are going to be stacked on top of each other, some just side by side. Anyway, the thing is, it's a partial positive to a partial negative. Okay, so let me draw another one. We could have CH3OH. Okay, and let me put this molecule on here. Okay, this carbon is bonded to that oxygen. It doesn't look like it, but it is. There's a bond there. Okay, so let's look at your carbon-oxygen bonds. Which one is more electronegative, oxygen or carbon? Your answer should be oxygen because it's closer to fluorine. So that gets your partial negative. Carbon will get your partial positive. So over here, carbon-oxygen bond. Oxygen will get your partial negative. Carbon will be your partial positive. Notice I'm not labeling any of the carbon-hydrogen bonds. Carbon-hydrogen bonds, they have about the same amount of electronegativity. So we say they're non-polar, meaning not reactive. So they'll never have that partial positive, partial negative. So there's never going to be an attraction there. So we're just looking at, and those are going to be your biggest bonds, you'll notice. But almost everything else has that positive and negative. So let's look at this. Where will the interaction take place? This negative here will be attracted to where? This oxygen will be attacked on this molecule. You should be showing the oxygen being attracted to this carbon. Okay? And though it's kind of far away, where will this carbon be attracted to? It's going to be attracted to this other oxygen there. Okay? So those are the two interactions there. So notice they don't have, like here I have the same molecule, but they don't have to be the same molecule. They can be different molecules as long as they have a partial positive and partial negative. The big thing you're looking for is, do they have a very electronegative atom in there? Okay? If it does, then it has a dipole interaction. Basically, anything but a carbon-hydrogen bond. Okay, so if we're just comparing, so this is a carbon chain. Okay, here's another carbon chain. Do you see, did I draw an oxygen or a nitrogen or a fluorine or chlorine coming off either one of these? No, that means it's only carbons and hydrogens. Even though you can't see them, just know that it is only carbons and hydrogens when you draw lines like this. It doesn't matter how you draw them. If there was like an oxygen on there, they would have to draw like OH. Okay, it would actually be on there. But let me take that off. Okay. So if they do not have an electronegative atom, like in these molecules here, there's no dipole interaction and there's only dispersion. Okay, dispersion only. But these up here, they have dispersion because everything has dispersion, okay? Your answer, so if I ask if something has dispersion, the answer is always yes, okay? But this also has a dipole interaction, okay? And which one is the strongest intermolecular force, typically we'll say? That is going to be your dipole, okay? So these molecules will have a higher melting or boiling point than any of these. Okay, so that is your dipole-dipole. You're looking for something with an electronegative atom in there. Now let's look at another one. Okay, let's look at these really quick. Which of these have a dipole force? So we have to look at, what's the word I'm looking for? Like the shapes, okay? So let's just look really quick. CH4, I already told you, if it's made up of just carbons and hydrogens, it's not going to be polar, so it won't have a dipole-dipole moment. There's no electronegative atom in there, so we don't even have to look at this one. So let's look at CH2Cl2 and CO2. CO2, when you draw it out, looks like this. There's lone pairs off the oxygens, but basically like this. What shape is this? Linear. Okay, do you see that this oxygen is actually, it's 180 degrees apart from that one? Okay, so when we were looking at polarity, was this polar or non-polar? Non-polar. Okay, these cancel each other out. All right, so this does not have dipole interactions. So if we look at CH2Cl2, so we might have an H, a Cl, and a Cl. Okay, these will not cancel each other out. Okay, they're not symmetrical. Okay, so this will have a dipole interaction. So you're going to have to look at your shapes and see, do they symmetrically cancel each other out? So basically, are they polar or nonpolar? If it's polar, it will have a dipole moment. Okay. Now let's look at the next intermolecular force, hydrogen bonding. Hydrogen bonding is basically a dipole interaction, but it's a special case. Okay, it's like a super dipole. And this is between hydrogen, okay, as the name implies, and oxygen, nitrogen, or fluorine. Okay, now this is important to remember. We're not actually looking at, if we look at this water molecule, we're not looking at the actual hydrogen bond between oxygen and hydrogen, okay? See, we're not looking at that bond. We're looking at the interaction to another water molecule, okay? You see the line here, the little kind of dotted line? Okay, that's the interaction. That's not an actual hydrogen bond when we think of like Lewis dot structures. This is just an interaction, okay? So what it is hydrogen's not very electronegative, okay? But oxygen, nitrogen, and fluorine, those are your three most electronegative atoms on the periodic table, okay? So they're very electronegative, so they get the partial negative. Hydrogen's kind of, it's pretty electropositive, so you get your partial positive, and so they're highly attracted to each other, and they give you a special sort of, like a super dipole. Okay, so again, so if I look at something like this, CH3OH, okay, with H2O, I'm just going to draw it like this. Okay, now on here, the water molecule, where's my partial negative? That is oxygen, because it's most electronegative, and my hydrogens will have the partial positive. Okay, now let's look at the oxygen here. Again, it's going to have the partial negative, and we're looking at the hydrogens, the partial positive. Okay, now where will this oxygen be attracted to on this molecule? Let me change the color here. It's attracted to, let's say that hydrogen, or you could have said this hydrogen, okay? And this hydrogen here, this partial positive, where is it attracted to on here? The oxygen, okay? Notice I'm just putting an attraction there, so it's like glue. They're attracted to each other. You know, they want to go on a date if you want. But I'm not looking at this bond right here, okay? That's a literal oxygen-hydrogen bond. But I'm looking at the intermolecular force called a hydrogen bond, okay? So I'm looking at the interaction here. And notice again, it's between two different molecules. I could have water molecules that it's attracted to. Let me see. I think I have... Yeah, so here, do you see the actual solid lines? Those are your actual oxygen-hydrogen bonds. Like these dotted lines here, these are the interactions. So there's all these interactions going on here. Hydrogen to oxygen, hydrogen to oxygen, hydrogen to oxygen, okay? So it's the hydrogen of one atom attracted to either an oxygen or a nitrogen or fluorine of another, okay? So it could be a nitrogen or a fluorine, just so you remember, okay? This is the strongest one we've looked at so far, hydrogen bonding. And if you look here, I want to show you this. Okay, so look at the molecular weight, and here are the boiling points. Okay, so let's just look at this trend starting here. So do you see that this has no hydrogen bonding? Okay, dihydrogen sulfide. This is dihydrogen selenium, dihydrogen deuterium. Okay, so look here. The trend is, as the molecular weight goes up, the melting point goes up, or if you want to look at boiling point, okay? So that goes up. Why? Because the intermolecular forces are stronger because more dispersion, okay? But look at water. So the trend should go down. It should be like a straight line, but all of a sudden water is way up here at melting point. Why? What's the difference between this and all of these? And the answer is hydrogen bonding. Do you see how much having hydrogen bonding affects the melting point? It's pretty drastic. I mean, this is a really, really strong intermolecular force. And again, that's the glue that holds them together. So they don't want to be broken apart. They want to stay together, so it takes a lot of energy to melt them. Let's look at this here. Which compound is a liquid at room temperature and why? Okay, so let's look here. We have a carbon bonded to oxygen and hydrogen. Okay, so let's first list all intermolecular forces with this one. Okay, does it have dispersion? Yes, because everything has dispersion. Does it have dipole? Let's see, do I have a very electronegative atom in here? Yes, oxygen, nothing cancels it out. So it has a dipole. Does it have a hydrogen bond? Okay, or what you're really looking at, does it have the possibility to a hydrogen bond? Okay, and so if it has the possibility, you have to have a oxygen, nitrogen, or fluorine bonded to a hydrogen. And do I have that? Do I have a hydrogen coming off of here so it could possibly hydrogen bond to something else? No. Okay, so this just has dispersion and dipole. Let's look at this one. Does this have dispersion? Yes, because everything has dispersion. Does it have a dipole? Well, we have a very electronegative atom in here, fluorine. Does anything cancel it out in terms of, polarity? No. So it has dispersion. Does it have hydrogen bonding or the ability to hydrogen bond? So it needs to have a hydrogen coming off fluorine. And the answer is no, because all the hydrogens are coming off carbon, just like in this one here. So let's look at this one. Does it have dispersion? Yes. Does it have, dispersion. Does it have dipole? Yes, because it has electronegative atoms. Okay. Does it have hydrogen bonding? Yes, or the ability to hydrogen bond, because this oxygen-hydrogen bond, that's what you have to look for, can have a hydrogen bond to something else, that intermolecular force. Or this could be a nitrogen or fluorine, okay? So the answer is this one's going to be a liquid because it has the strongest intermolecular forces. So it's going to hold everything together. The last one is an ion dipole. This is the easiest one to recognize. Let me pull up the picture here so you can see it better. You literally will have an ion, or an ion is just a charged particle. So do you see I have sodium right here and chlorine right here? Okay, so I have a charged particle, and it's going to be attracted to something which has a dipole interaction, or a possible dipole. So that's where you get ion dipole. So water is polar, okay? So this is a water molecule. Those bluish, greenish area here, that's oxygen, and the black ones are hydrogen. Okay, so let's think about this. So the chlorine is a negative charge, okay? So is it attracted to the hydrogens or the oxygen? Okay, just think about batteries or magnets, Okay, you're looking for something with a partial positive, and that would be hydrogen. Do you see how the hydrogen little feet are pointing towards it, and in all of these, the hydrogen feet? Okay, because the chlorine is attracted to those partial positive hydrogen. Now let's look at the sodium. The sodium has a positive charge, so what on the water molecule is it attracted to? The oxygen, because the oxygen has a partial negative, so you see all of the little oxygen little heads are pointed towards the positive. Okay, so ion dipole is easy to recognize because you literally have a full positive or negative in there, not a partial positive or negative, a full positive or negative. Here's a summary. Let me pull this back up. So here's the dispersion. All molecules and atoms have it. Okay, and that's just the protons of one atom attracted to the electrons of another. Polar molecules have dipole-dipole interactions. So you see here the partial negative of one, this is like an oxygen, is attracted to the partial positive of another, and this is like a carbon. Hydrogen bonding, so molecules containing a hydrogen bonded to fluorine, oxygen, or nitrogen have the ability to hydrogen bond. And then our strongest interaction here is whenever you have an ionic compound, something with a full charge, in there with something with a polar molecule. Sorry, that is my cell phone. So this is the order of strength. Ion dipole is the strongest, then hydrogen bonding, then dipole, then dispersion. Okay, so let's look at some examples and let me see if we can figure out, here we go, which one will have the highest interaction here. So let's just do a few examples. This one's running a little long. So if we have And let's do one more. Okay, so let's list these in the the highest to lowest. Okay, first of all, do you see this has a positive sodium and with water? So anytime you see like a full positive, negative charge in there, that's going to be the highest. And what is the strongest intermolecular force that it has? That's going to be the ion dipole. So this has an ion dipole. So this is the strongest. We'll say this is number 1. Now which one? Anything else have ion dipole? No. So let's look at the next. That would be hydrogen bonding. Do any of these have hydrogen bonds? Yes, this one here. So this is the next one because it has a hydrogen bond. Okay, now let's look at all 3 of these, of here, here, and here. So let's look at the next intermolecular, or do any of these have hydrogen bonding? No, so let's look at the next intermolecular force. That would be dispersion. Does this have a polar molecule in there, so very electronegative? No. Anything electronegative? No, because it would be listed on there. Anything electronegative? Yes, this chlorine is very electronegative. So this one's going to be number 3 because of dipole. Okay, now what about these 2 here? Do these have dipole? No, we already said they don't. So this one has dispersion. Okay, this one has dispersion. Okay, but which one would be higher? Which one would be number 4? Here or here? So let's look. Do you see how this one has a branch? Yes. They're about the same size, but this one has a branch. So this one will be number 4, and this one will be number 5. And the reason this is 5 is because branching. Okay? Now listing these, basically you've listed which one would have the highest boiling or melting point to the lowest. So the highest one would be number 1, and the lowest would be number 5.